Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, Alhamdulillah, we will continue today's session with beam analysis using stiffness method or stiffness matrix method. Okay, so we will look into the beam analysis. You focus on indeterminate beam. Okay, how we actually establish the element stiffness matrices for beam, establish the structure stiffness matrix, and after that we how we actually identifying the displacement, the unknown displacement, unknown reaction, and lastly we will use the reaction that we determine from the analysis to draw the shear force diagram and bending moment diagram. Okay, basically using beam, okay, the difference between beam analysis and thrust analysis, the one that we have learned previously, is due to the degree of freedom. Degree of freedom, because in beam we have two degree of freedom in y and z component. Okay, do you still remember in thrust analysis we have two degree of freedom in x and y component, because we don't have to consider the moment. There is no moment in thrust, there is no fixed support in thrust, so we just have to calculate the horizontal and the vertical deflection, as well as horizontal and vertical displacement and reaction, horizontal and vertical for thrust. Okay, however, in beam, we have to consider the degree of freedom in two component, but it is in y component and in z component. Okay, because in beam analysis, as far as we know, the horizontal displacement in beam will be zero. The horizontal displacement will be zero, and if we consider the fixed end in beam, the reaction in x direction, ax value, cx value will be zero. So that is why we don't have to consider x component in beam, but we have to consider component in y direction, y component, and in z component. Okay, always remember, degree of freedom, we must always look at it in terms of displacement, and in terms of displacement and in terms of forces. Okay, so y means deflection, vertical displacement, as well as vertical force, and z means rotation and moment. Okay, let's look at the question first before I explain about the concept later on. Okay, so this is an indeterminate beam. This is an indeterminate beam. There are two members or two elements. Okay, member AB and member BC. Okay, in stiffness method, actually, you have to be able to know how we identify node. Okay, how we identify node. For example, you are looking at this beam. Okay, at point B, AB and BC, has different EI. AB has 2 EI, BC has another EI and 2 EI. So that is not constant. So that is why B we have to consider as node. We have to consider as node because of the difference between EI for AB and EI for BC. Another thing that we need to consider when we identifying node is whenever at that point there is point load. For example, we can see that at point B there are two type of loading. Okay, one is point load, vertical force at B, So vertical force at B is in Y component, and moment at B is in Z component. So because of these two reasons, we have to put B as node. Okay, we have to put B as node. Okay, so the question look like similar with trust because we have to start with establishing element global stiffness matrices. Means it is K for element. K for element, K1 and K2 in this case. AB is element number 1 and BC is element number 2. Okay, after that, we will combine K1 and K2 to produce the structure stiffness matrix. K1 plus K2, we will produce capital K or structure stiffness matrix. Okay, next is calculate unknown displacement. And in order to calculate unknown displacement, of course, we have to have the stiffness equation or force displacement equation. Q is equal to KD. And for beam, normally beam has UDL, right? Okay, UDL 9 kilonewton per meter along member AB. And when this case happen, okay, because remember the definition of Q, nodal forces, and 9 kilonewton per meter is not subjected directly at nodes. It is member load, member that is subjected to loading. So we have to distribute it to nodes first, and we call it as equivalent nodal forces. Okay, and once we have finished writing the force displacement equation, then only we can solve unknown displacement or non-zero degree of freedom. After that, using displacement, unknown displacement, we will solve the unknown reaction, and after that we can continue to draw shear force diagram and bending moment diagram. Okay, before we continue this, continue to solve this. Okay, these are important things that everyone should understand. Okay, looking back into this diagram, okay, there are three nodes A, B, C. A, B, C, three nodes. Okay, three join, A, B, C. Okay, you can use label as A, B, C, or we can use label as 1, 2, 3, doesn't matter. Okay, okay, number two, there are two degree of freedom per node. Okay, there are 2 degree of freedom per node. Beam has 2 degree of freedom per node in X, in Y and Z component. Y and Z component, we don't have to consider X. So AX at fixed, we don't have to consider. We just need to consider Y and Z component. Number 3 actually, 1, 2, 3, number 3. There are in total 6 degree of freedom. 6 degree of freedom because look at this beam. There are A, B and C. Okay, A, B and C is 3. Okay, 3 nodes, 3 join. So 3 times 2, we get 3. We get 6. 6 degree of freedom. So in total, we have to label 6 degree of freedom. Means from 1 to 6, we have to label it according to unconstrained and constrained degree of freedom. Remember, we have to label start from unconstrained because in unconstrained system, there are unknown displacement, and in constrained system, there are unknown reaction. Okay, so okay, looking into this, actually there are two unknown displacement and 4 unknown reaction actually. Okay, some typo here. Three unknown reaction. No. It is 2 and 6. Okay, let me explain you in detail. Okay, so we move to this. Before we analyze the example as given, so let me introduce you one simple beam like this first. Okay, this is a continuous beam. Okay, this is a continuous beam because I want to explain the concept. So let's say this is beam. This beam is the beam that you always see. Okay, whenever you analyze continuous beam using flexibility method. Okay, so basically it is like this: A, B, C. This is 10 kilonewton per meter. This is 10 meter and 10 meter. Okay, so I want to introduce you about degree of freedom. Okay, that we should apply. Okay, at each node. So we will need to label two here, two, and another two. Okay, because in total there are 6 degree of freedom we get from join in Y and Z component. Okay, Y and Z component. So there are 6. Okay. In trust analysis, we have to label 5 things in the diagram. 5 things. 5 things including number one. Number one is, remember, node number. Number 2 is element number. Element number. Number 3 is degree of freedom. So we have to label according to unconstrained and constrained. Number 4. Number 4 is we have to put arrow. And number 5, we have to put coordinate. Okay. Number 4 and number 5. Okay. This 4 and 5. Actually, we need to do this, to put this, to label. Okay. Just for truss and frame. But we don't have to put arrow. We don't have to put coordinate in frame. Okay, we don't have to put arrow and coordinate in frame. Okay, that is because we put arrow and we must have coordinate whenever we need to find cx and cy. In the formula of k in trust, we have to have cx cy. We have cx cy in the formula. That's why we have to have arrow and coordinate. Same goes to frame. There are Cx and Cy in K formula. However, in beam, there is no Cx, Cy in the formula. In the K formula, there is no Cx, Cy. Okay, there is no Cx, Cy. Okay, look at the formula. So this is the formula. Okay, and inside the formula, so this is actually the formula to calculate element stiffness matrix in beam element. And in this formula, there is no CXCY. There is no CXCY. So when there is no CXCY, we don't have to put coordinate. We don't have to put arrow. And in beam, actually, it has same local and coordinate. K prime is for local system. K is for global system. We are referring to the global coordinate system. So we refer to K. K, not K prime. It is K. Okay, and inside this, we can find that the stiffness in beam, the stiffness is beam influenced by E, the material, the modulus of elasticity. Okay, it is called as material properties in the software. I, section properties or moment of inertia, as well as length of each member. So this is the formula to calculate stiffness in beam. So okay, going back to this. So we don't have to have 4 and 5 in beam. So we need to focus on how to label degree of freedom according to unconstrained and constrained system. That is very, very important. Okay. So let's say we want to sketch the beam. Okay, 2 beam, because one is for unconstrained and one is for constrained. Okay, this is unconstrained. Okay, UC for unconstrained, C is for constrained. Okay, this step in beam is very, very important. Okay, look at the diagram. Okay, look at the diagram. Okay, looking into this. Okay, looking into this, A is fixed. A is fixed. So fixed has three unknown reaction. Fixed has three unknown reaction in X, in Y, in Z. So we only count two here. Two. We only count two unknown reaction at A in Y and Z component. So we have to put two Y and Z at constraint system. Y and Z, because we don't have to consider X, we only count two. Okay, it is due to fixed support at A. Okay, and then at B, it has BY. At C, it has CY, reaction at the support. We have, okay, we can find that there are BY and CY. BY and CY are the reaction at point B and at point C, respectively. So we have to put, okay, this is the arrow for BY and this is the arrow for CY. Remember, because this is constraint. Constraint means in the system there are unknown reaction. Okay, unknown reaction. Here is U, unknown reaction. Unknown reaction. Okay, QU. Okay, now we have put four. We have put four in constraint system. And we know that we have to have in total six. In total, we have to have 6 degree of freedom. Okay, we have 3 points, 3 nodes, 3 join. Okay, so at point number 1, at A, okay, 2, we have put in constraint. So we don't have to put anything else. Okay, this is A, B, C, A, B, C, A, B, C. So at point B, only one, okay, have been put in constraint system. So we know that we have another one, okay, because we must complete two at each node, two at each node. Okay, the remaining is in Z component. Okay, and we have to put the same at C. So now there are 6 degree of freedom, 2 in unconstrained and 4 in constrained. So for unconstrained, this 2 degree of freedom means 2 unknown displacement. So this 2 degree of freedom, okay, means unknown displacement. So it has 2 degree of freedom in unconstrained system and 4 degree of freedom in constrained system. 2 and 4. Total is 6. Total is 6. Okay. So now we have to label. And when we label, we have to label 1 and 2. One must be started in unconstrained. So we label 1, 2. Okay, 1, 2. We label 1 and 2. Okay, then we have to follow the remaining. Okay, the remaining. So we label 3, 4. Okay, normally when we have in full Y and Z, we will start with Y. Okay, we will start with Y. Okay, 3, 4. Okay, and then continue with 5 and 6. So we have now 6 degree of freedom label. We have label according to unconstrained and constrained degree of freedom system. Okay, so in the main diagram, if we relabel, okay, all this, so we will get 3, 4, 5. This is 5, 1, and 6, 2. Okay, 3, 4, YZ, 3, 4. Okay, at 1, at node 1, at A, okay, YZ is 3, 4. YZ is 3, 4. Okay, at B, YZ is 5, 1. YZ is 5, 1. And at C, YZ is 6, 2. YZ is 6, 2. Okay? Okay. So for the element, for element stiffness matrices, it has 4 degree of freedom. 4 degree. We will produce K 4 by 4. So in this 4 by 4, of course, still we have to identify near and far end, near and far end. And for beam analysis, for beam determinate or indeterminate beam, when we analyze using stiffness method, we always assume that the beam is going towards right direction. Okay, the arrow is always moving towards right direction like this. That is why, okay, we don't have to put arrow because the blue direction shows, okay, means that for every beam question, even though we don't put the arrow, we assume that the arrow is always moving towards right direction, so that A, between A and B, between element number 1, A, B, A will be near, B will be far end for everyone. Okay, A will be the near end, B will be the far end. So to calculate K1, okay, we will produce K in terms of EI. In terms of EI, it is 4 by 4 matrix. 4 by 4 matrix because one element consists of 2 node. One element consists of 2 node. This is element number 1 between A and B. Okay, element 1 between A and B. And at A, it is 3, 4 and 5, 1. 3, 4, 5, 1. This is the label. This is the label. For near is 3, 4. For B, for far is 5, 1. So this label will be put in the matrix K1. 3, 4, 5, 1. 3, 4, 5, 1. Using the formula, okay, we find the value. Okay, of course, we have to put EI outside. EI remain, make EI constant. Okay, and then we find the value inside the matrix. What most important is the label that we put. Okay, this must be correct. Okay, this label must be correct. Okay, 3, 4, 5, 1. 3, 4 in A, 5, 1 in B. This is compulsory. 3, 4, 5, 1. 3, 4, 5, 1. This is compulsory in beam. Okay, 3, 4, 5, 1. Then we will repeat the same for K2. For K2, we will repeat the same. Okay, for K2, we will repeat the same. K2. Okay, in terms of EI, we will produce 4 by 4 matrix using formula. Okay, so element number 2, B to C. B to C, the label used is, okay, 5, 1 for near end and 6, 2 for far end. Okay, please try to label it correctly. Okay, because if you don't label it correctly, okay, everything will be wrong. Okay, so we label according to near and far end. It is 5, 1, 6, 2. 5, 1, 6, 2. 5, 1, 6, 2. 5, 1, 6, 2. Okay, start with near. 5162, 5162. Okay, and after that, once you have got K1 and K2 like this, we will combine. Okay, it is the same procedure like what we have done previously in truss. Okay, Okay, K we will produce in terms of EI, it is 6 by 6. 6 by 6, we label start from 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that is how we produce. Okay, that is why we produce the, okay, the element global stiffness matrices K1 and K2. K1 and K2. Okay. Okay, now before we continue back to the question given, okay, in the slide, so we focus on this beam. Okay, we settle part the first part where we establish the element stiffness matrices and the global the element stiffness matrices and the structure stiffness matrix K1 and K2. We combine these two, we get K. Okay, the formula is given, but so all this, the most important thing is we label degree of freedom correctly. We have to. Okay, so it must be started. Number one must be put in unconstrained system followed by constrained system. Okay, so this 6 degree of freedom actually refers to displacement and refers to forces. So we will have D1 until D6 and Q1 until Q6. Okay, so we move to the next part that everyone should understand about the stiffness equation. About the stiffness equation in beam. About the stiffness equation. Okay, about the stiffness equation. And in beam, we will use Q is equal to KD plus Q naught. Q is equal to KD plus Q naught. Okay, what is Q, what is K, what is D, what is Q naught? Okay, so Q as usual, Q is called as nodal forces. Nodal forces. Nodal forces means forces that is subjected directly at node at 1, 2, 3, 4, 5, 6 directly. Okay, forces. It is vertical force or moment. Vertical force or moment in beam. Okay, and then K is a stiffness matrix. Stiffness matrix. D is nodal displacement. D is nodal displacement. D is nodal displacement. Okay. Six value in vertical direction. In y direction, it is vertical displacement, and in z component, it is rotation D. So there are 6 value of D1 until D6. D1 until D6. And in beam as well, we have to have Q naught whenever okay, the element or the member is subjected by uniformly distributed load. Means that member the member is loaded with force on the member. So because it is not Q means forces that is subjected directly at nodes at 1, at 2, at 3. But when we have UDL, it is not Q. UDL is force that is subjected on the member. And what we need to do is we have to distribute it. We have to distribute it equivalently to the nodes. And we call this as equivalent nodal forces. Equivalent nodal forces. It is equivalent nodal forces. Q naught. Okay, equivalent nodal forces. Okay, so the equation will be like this. Q K, this is D plus, okay, 6 value. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. 6 value. Okay, here is D1. Here is D1, D2. D1, D2. Okay, D1, D2. Okay, recall back what we have learned previously under trust analysis. Okay, we have to be able to put the value from the diagram in the equation. Okay, so but before that, looking back to this, okay, we have to be able to see that this numbering we use is representing forces or displacement. Forces or displacement. For example, if it is D1, what does it mean? D1, D2, D3, what does it mean? Okay? So we have to be able to see that D1, if we look into this diagram, D1 is in Z component. What does it mean? Okay. It is actually like this. We have to relate with displacement. Okay, draw the diagram. Okay, draw the diagram. So this diagram, okay, due to loading, this is support, right? Due to loading, it will deflect. So it will deflect like this. Okay, this is deflection. Okay, deflection. So at each point, so remember that it is in Y and Z component. So Y component as displacement, this is delta and theta. Delta and theta. And for Q, okay, for Q, Y component is the force, the vertical force V. The vertical force V and the moment. The moment. That is between D and Q. D is displacement. Q is force. Displacement and force. Displacements and forces. Okay, there are two components, Y component and Z component. That is degree of freedom. Okay, so in Y component, in terms of displacement, it is delta. Okay, and in Z component, in terms of displacement, it is theta. Okay, so tengok this diagram. Look at this diagram. Okay, at fixed support, okay, delta and theta. What is the value of theta? What of the value for delta? Okay, in terms of, okay, looking at this, okay, so I have drawn I have sketched the deflected shape of the beam. Okay, the behavior. Okay, the behavior. So looking into this, so we find that at fixed support, this delta is 0. There is no vertical deflection at fixed, and there is no rotation at fixed. Because it is fixed support, no movement. That is why when we draw the deflected shape for fixed support, we cannot draw until the support. We cannot draw until this point. Okay, because it is fixed. Delta is 0. The delta is 0. Theta is 0. This is for fixed support. Okay. So move to point B, roller support B. Okay, delta and theta. Delta and theta. Okay, for delta, Okay, delta is 0 because no vertical movement. Because of roller support, there is no vertical movement. Okay, because of roller support. There is no vertical movement. So the delta at B is 0. 0. But the theta, remember theta we measure from the tangent line of the curve. Okay, theta, this is theta. This is theta. Okay, the tangent line, the angle, and we measure from the tangent line. Okay, should be the same size. So this is actually theta at B. Theta at B. Theta at B. So theta at B is not 0. Theta at B is not 0. Okay, the rotation. It has rotation. It is unknown. It is unknown. This is not 0. This is unknown. Okay, so this is not 0. Okay, this is what we call unknown displacement. This is unknown displacement. Okay, unknown displacement. Okay, at C, delta and theta. Delta and theta. Remember, delta and theta is actually Y and Z component. Y and Z component. Okay, there is no vertical movement at roller support C. Again, this is 0. This is 0 and we can see the tangent line, right? We can see the tangent line. Okay, this means okay, the right one must touch the roller. Okay, so it is theta at C. So this is theta at C. Okay, theta at C. So this theta at C is unknown displacement. This is not 0. This is unknown displacement. Okay, from this, there are 6, right? 6. 2 at A, 2 at B, 2 at C. Okay? And from these 6, there are 4 zero value. There are 4 zero value. Okay, which is actually representing the support position. And that is why between unconstrained and constrained, remember, unconstrained DOF system and constrained DOF system. Okay. Okay, this is in this table. Okay, constraint means support. At support displacement 0. Constraint means support at support displacement 0. Constraint means support. Constraint means support. At support displacement 0. 0. Okay? Constraint means support at support displacement 0. So D that we label in constraint start from 3, 4, 5, 6. 3, 4, 5, 6. 3, 4, 5, 6. So what does D3 mean? What does D4 mean? What does D5 means? What does D6 means? Okay? D3, D4. D3, what is D3? What is D3 and D4? D3 and D4, this. D3 and D4. D3 and D4. Okay? D3 and D4. D4. Do you get that? Okay, D3 and D4. D3 and D4 because when we label, okay, so this is 3, 4, 5, 1, 6, 2. 6, 2. 5, 1, 6, 2. 6, 2. So D3 and D4, D3 means delta A. D4 means theta. Theta at A. Theta at A. So that's how we see, okay, the label. It is not just label 1, 2, 3, 4, 5, 6, but we have to be able to imagine the behavior. Okay, we have to be able to imagine the behavior. D4, what is D4? D4 is delta at A. At delta, yes, delta at A. Okay, so it is D3. D3. D3 means delta at A, and this is 0. Okay, we cannot just look at this numbering as numbering. Cannot. Okay, we must be able to look at the behavior. Okay, D3. D4. D4 is rotation at A. D4 is rotation at A. Okay, so it is theta at A. Theta at A. So this is very, very important. So if you understand this, actually you don't have to remember. But if you don't understand about this, okay, you have many things to remember. Okay, please try to understand, not remember. Okay, this is D3, D4, D3, D4. Okay, D5, D6. What does it mean? D5, D6. D5, D6. Okay, at point B, delta at B is equal to 0. Delta at B is D5. Delta at B is D5. So D5 is delta at B. Delta at B, and this is also 0 because of roller support. D6 is delta at C, and this is 0. Okay, so that is how we analyze, okay, the value of D3 until D6. Okay, now this is for constraint. So the remaining is 2, 1 and 2. So what does D1 and D2 means? What does D1 and D2 means? Okay, looking back into this, okay, D1, Z component. Okay, we understand that D1 and D2 in unconstrained will be the unknown displacement. Unknown displacement. So what is that? Okay, what is D1? What is D2? Can we illustrate by diagram? It represent what? Okay, so looking back into this diagram, okay, D1, D2 representing theta at B and theta at C, means rotation at B, rotation at C. That's D1 and D2. So D1 is theta at B. D2 is theta at C. So this is du, unknown displacement. Unknown displacement, D1 and D2 in Z component, it is rotation. So the unit should be in radian. Okay, because it is representing rotation. If in Y component, it should be in meter, but this is actually representing rotation. Rotation, so it is in unit radian. Okay. So that is how we read the information from the diagram. Okay, same goes to Q. So Q also, we have Q1 and Q2, and we have Q1 and Q2. Here Q3, Q4, Q5, Q6. Okay, Q1 and Q2. Q1 and Q2 means moment. Q1 and Q2 means moment. Okay, Z component 1 and 2 Z component. Q1 means moment at B, and Q2 means moment at C. Moment at B, moment at C. So look back into the diagram. Okay, fine. Is there a moment subjected at B? If there is no moment, okay, if there is no moment in the diagram, applied moment in the diagram, so we just need to put 0. Okay, 0 for Q1, 0 for Q2. Unless the applied moment is given at that point. Okay, because this is unknown, so we have to put value because the condition is opposite. So this is 0, 0 representing moment at B, moment at C. And remaining, okay, remaining 3, 4, 5, 6, 3, 4, 5, 6. This will be for the vertical, it is AY. This is AY actually, AY. 3 is AY, 4 is MA, 5 is BY, 6 is CY. So these are the 4 unknown reaction. 4 unknown reaction in the beam. 4 unknown reaction in the beam. Why 4? Because we don't have to consider X, AX. Because AX is 0. 4 unknown, 4 unknown reaction. It is 4 unknown reaction. Okay? Okay, this is very, very important. I want to understand this very well. Okay, so this is how we illustrate the definition of Q1 until Q6 and D1 until D6. D1 until D6. Okay, I think for night session, I want to explain about equivalent nodal forces Q naught. I don't want to explain about that right now. I want you to look at look at back to all this and try to understand the analysis of beam using stiffness method. So remember what's the difference between beam and truss. Okay, so this is conventional type of beam whenever we analyze this beam using flexibility method. Okay, but in stiffness method we have to analyze using formula. And before we analyze using formula, most important thing is we have to label the degree of freedom correctly. And for beam, we don't have to put arrow and we don't have to put coordinate, because arrow, understood, the arrow is always moving towards right direction. Okay, we don't have to put coordinate because we don't have to calculate CX and CY. The beam, the stiffness for beam, okay, the stiffness the stiffness K for beam will be depending on EI and length only. Okay, not CX, we don't have to calculate CXCY. So based on the formula, we will establish K1 and K2. And for K1 and K2, it is just simple formula. But the most important thing is we have to label it correctly according to near end and far end condition. Near YZ, far YZ. We have to label it correctly. 3451, 3451. For K1, and 5162, 5162 for K2. So once we have this, we have to continue as usual, as previous procedure in trust. we have to combine K1 and K2 to produce the structure stiffness matrix. Remember the definition of stiffness method. One of the procedure is we need to divide the system into element. System in structure, we have to divide the structure into element. Then only we can produce the structure stiffness matrix. So that is how that is how we analyze this. Okay, we divide the system. The system is the capital K. Okay, the system is capital K. We divide into element. Element 1, element 2, K1 and K2. K1 and K2, please label it correctly. Then we produce the structure stiffness matrix K, 1, 2, 3, 4, 5, 6, and it must be written in order. Okay, it must be written in order. So once finished, okay, we finish establish the global the structure stiffness matrix. Okay, but in order to calculate the unknown displacement and unknown reaction, we have to understand what is nodal forces, nodal displacement, and equivalent nodal forces. Okay, so nodal forces is forces that is subjected directly at nodes. We read from the degree of freedom level. Same goes to nodal displacement. But for equivalent nodal forces is quite different, because equivalent nodal forces, we have this. We use this whenever in the question there are UDL, because UDL is loading that is subjected not at node but on member. So when member has loading, we have to distribute it equivalently to node. Then only we can write in full like this, the stiffness equation in full. So we have to put all Q1 until Q6, D1 until D6. So whichever zero value we have to put into this. Okay, and we will have to produce Q naught 1 to 6 position as well. So for Q naught equivalent of the forces, I will continue to explain to you by tonight session. Okay, so please try to understand. So this is very, very important, very, very important. So please make sure everybody understand about this and how to illustrate this. Okay, because you have to be able to see the D1, D2 until D6 not as numbers, but as the behavior. Okay, so for this, it is 0, 0, Q3, Q4, Q4, Q5, Q6. Okay, because 1 and 2 representing moment at B and C, there is no applied moment given in the question. It is 0, 0. Okay, K. Okay, produce after this on your own, because we have remaining 1 hour time, right? And for D1, D2, it unknown displacement, rotation at B and rotation at C, but remaining 0. Okay, because there is no deflection and rotation at support. Okay, so please complete this by another 1 hour session. K, K, because tonight we will concentrate on this. For tonight, we will find the value for this, and after that we will solve for the unknown displacement, and unknown reaction. 2 unknown displacement value and 4 unknown reaction values before we close the analysis, with drawing the shear force diagram and bending moment diagram. Okay, so I will set the attendance link in the future after this. Okay, please tick your attendance. All 14 of you, please tick attendance, and please complete the K. The K, I will give you I will put the formula in the OneNote class notebook. The K formula. Okay, the K formula. So please complete the structure stiffness metric, and by tonight we will complete this stiffness equation. Okay, so that's all for this session. Thank you very much. Thank you very much. Inshallah, we will continue the session. Wait for the link given. Yeah. Okay. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.